Nikolai Bogdanov-Belsky's 1895 painting depicts a rural Russian schoolroom. The teacher, Sergei Rachinsky, retired from university to educate peasant children in mental arithmetic. The chalkboard displays a specific fraction, the sum of 5 consecutive squares divided by 365. The children solve this equation without paper or slate, holding the entire sequence of squares and sums in their working memory. These students are roughly 10 to 14 years old. Solving this requires a level of computational fluency that challenges most educated adults. This scene documents a systematic pedagogical framework that achieved consistent results across an entire village school. A standard algorithmic approach to this problem requires squaring each term individually: 100, 121, 144, 169, and 196. Mental arithmetic fails here because the working memory load is too high. Holding these 5 three-digit values while trying to sum them sequentially creates an immediate cognitive bottleneck. Sergei Rachinsky's 1891 textbook, 1001 Problems in Mental Arithmetic, offers a different path. The curriculum relies on a complete intuitive fluency with the properties of the first 1,000 integers. Rachinsky trained his students to recognize mathematical structures that bypass the need for brute force calculation. Number familiarity is the ability to decompose integers into prime factors and sums of squares at sight. For these students, the number 365 possessed a specific mathematical identity beyond being the number of days in a year. At its base level, 365 is the product of 5 and 73. Its more useful identity is the sum of 3 consecutive squares. 10 squared is 100, 11 squared is 121, 12 squared is 144. Summing these yields exactly 365. There is a parallel identity. The next 2 squares in the sequence also sum to 365. 13 squared is 169, and 14 squared is 196. Adding 169 and 196 returns that same value. Structural knowledge allows the solver to see the chalkboard problem as a geometric pattern. Arithmetic becomes a task of spatial recognition. Rachinsky's word problems were algebra problems presented as rural commerce. Problem 104 asks the student to solve for 3 items, where each costs 5 times more than the last, with a total of 248 rubles. Solving this requires constructing a geometric progression within the working memory. This chart assigns x to the ring. The chain is 5x, and the watch is 5 times that, or 25x. Combining the parts gives a total of 31 units equal to 248 rubles. The final division resolves through simple multiplication. 31 goes into 248 exactly 8 times. The ring costs 8 rubles. The student then distributes that 8 back through the progression, finding 40 rubles for the chain and 200 for the watch. This exercise forces the brain to simultaneously store a base variable, apply a scaling rule, and track an aggregate total. Pre-revolutionary Russian weights and measures provided a layer of constant modular conversion. Unlike the metric system's base 10 shifts, these irregular units required active mental translation. Silver was measured in funts and zolotniks, where 1 funt equaled exactly 96 zolotniks. Problem 226 uses these units to create a proportional algebra problem. If the cross is x, the lamp is 3x. The candlestick is 4 times that lamp, or 12x. The total weight of all 3 items is 16x, which the problem equates to 1 funt. To find the solution in whole numbers, the student must recall the conversion factor and substitute 96 zolotniks for the funt. 16 goes into 96 exactly 6 times. Constant operation in base 16 or base 96 develops spatial grouping skills. This friction builds an algebraic intuition that simplifies standard arithmetic. Now we return to the classroom of 1895 and the fraction on the board. We solve this by applying the specific identities learned in Rachinsky's curriculum. The first 3 terms, 100, 121, and 144, sum to 365. The remaining 2 terms, 169 and 196, also sum to 365. The numerator is revealed to be 365 plus 365, all divided by 365. The equation resolves to 2. The student in the painting has recognized a mathematical symmetry. The squares are distributed around the denominator in a way that eliminates the need for complex addition. Rachinsky's problems prioritize structural recognition over rote memorization. The method provides a framework for parsing variables and recognizing prime structures without external aids. Mathematical proficiency is the ability to recognize the underlying structures that simplify data before the calculation begins.